Okay, it's Thursday. We're back here continuing with our chapter 29, which is magnetic fields. We started the other day, yesterday, by discussing the concept of magnetism and the magnetic field. Okay, and the magnetic field is used, it's a convenient way of describing the interactions between the magnetic interactions between charged particles, just like the electric field was used to describe the electrical interactions between charged particles. We also briefly touched on the fact that the charges need to be moving in order to experience magnetic effects, okay, either to produce magnetic fields or to experience magnetic forces due to the fields of other particles. Today we're going to develop equations for the magnetic fields of a point charge, a moving point charge, which serves as our basis for more complicated charge distributions. And this is completely analogous to when we develop the equation for the electric field of a point charge and then use that to come up with more electric fields due to more complicated charge distributions. So we'll focus on a single moving charge, a point charge, and then we'll focus on a long straight wire, and then we'll do a few other configurations tomorrow. Again, quiz 4 will be Monday in class covering homework 9. Homework 11 due date is next Saturday night. That deals with this chapter 29, and Unit 3 exam is next Monday, 4/19, in class. So, just like electric fields, charges are the sources of magnetic fields. The main difference, though, is that charges can be stationary and still produce electric fields, whereas only moving charges can create magnetic fields and experience magnetic forces. So we'll study today and Monday the magnetic fields due to three important sources: a long straight wire, a current loop, and a solenoid, which is a coil of many turns of current carrying wire. And we can model more complicated cases using these three cases as building blocks. Before we do any of these, we need to first start by studying the magnetic field of a moving point charge. And this field is very small, and it's not as important as the other three, but it does serve as the foundation from which all of the other ones are derived. So once we get the field for a single moving charge, a point charge, we can apply superposition due to all of the fields due to all of the moving charges to get the total field. So let's start with a single charge. And here's the picture. So you have a point charge Q, it's moving with some velocity V, and we want to evaluate the magnetic field, both the magnitude and the direction, because it's a vector, at some point R, where R is the distance from the charge to where we're trying to evaluate it, and the direction originates at the charge and ends at the evaluation point. So this vector R starts at the charge and continues to the evaluation point. And we want to calculate the magnetic field at that point. We're not going to derive this. Part of it is experimentally determined, but the equation which gives the magnetic field due to a point charge is called the Biot-Savart equation, and that this is for the magnetic field of a point charge. Okay, so looks somewhat like the equation for the electric field of a point charge, right? You have 1 over r squared, so that means that every time we double the distance, the magnetic field strength is 4 times smaller. It has this constant mu naught, whose magnitude is 4 pi times 10 to the negative 7. and we'll get into the units in a minute. And so that plays the role of epsilon naught. This is the magnetic permeability of free space. Epsilon naught, which was in our equations for the electric field and the electric force, is the electric permittivity of free space. So this is our analog for magnetic fields. Q is the net charge on the object, V is its velocity, and this unit vector R is a vector of magnitude 1 pointing along the direction of R. And we discussed unit vectors in the last lecture, so if this is a difficult subject or difficult topic, go back, review it, and stop by in office hours. The units of magnetic field are the Tesla. No, not named after Elon here. Where 1 Tesla is the equivalent of 1 Newton per amp times meter. So really goofy units. Magnetism, the units get pretty complicated. And there's that cross product again. So the magnetic field is in a plane, the direction is in a plane perpendicular to the plane containing the velocity vector and the vector r, and its direction is given by the right-hand rule. So this is why we studied cross products yesterday in lecture. So the magnetic field, the direction is given by the cross product here. Unlike the electric field, if we plug in V equals 0, meaning the particle is at rest, there's no magnetic field. It equals 0. So here are some typical field strengths. The surface of the Earth, the magnetic field strength at the Earth's surface due to the currents, the molten currents in the interior of the Earth, the field strength is about 5 times 10 to the negative 5 Teslas. And that's a really small number, and so sometimes you'll see units of Gauss instead of Teslas for small magnetic fields such as that of the Earth, okay? We're not going to use Gauss too much, but you might see these sometimes when you're out working. 1 Gauss is 10 to the negative 4 Tesla, and so the Earth's magnetic field strength in units of Gauss is about 0.5 Gauss. So that's a small field. The magnet on your refrigerator is about 100 times greater in strength than that of the Earth, but still pretty small. Then you get into these laboratory magnets that get larger, and these superconducting magnets, you get real high field strengths. So don't worry too much about Gauss other than if you ever see it, 1 Gauss is 10 to the negative 4 Tesla. Okay. So now we can also, so if we have V and if we have R in Cartesian coordinates, we can compute the cross product as we did the other day, and we'll do another example shortly, using the coordinates of each. Sometimes you may instead be given the speed of V along with its direction, and the distance r along with the direction, and the angle in between them, and then we can use this equation, which is the magnitude of the cross product is u naught over 4 pi times the magnitude of q times the magnitude of v. Magnitude of r is 1, and the sine of theta in between over r squared. So sometimes if you're given the magnitudes of these q and r, and you're given the angle between, we can use the other definition of the cross product. This is the magnitude to get the magnitude of the field, and then the direction is given by the right-hand rule, where we curl V into R, and the thumb gives the direction of B. So let's practice a little bit with the right-hand rule here, just to get the direction of B due to a moving charge. And these are 2 different views of B. One of them is, so you have this particle moving to the right, and it's positively charged. And the other one has the velocity going into the page, okay, as if you're looking at it from behind. And so I encourage you to stop here and practice using the right-hand rule. So for example, if we're looking at the field over here to the left, then R goes from Q to this point. So R is a vector going from Q toward the left, and V is into the page. And when you do the cross product of V cross R, you get a vector that's pointing perpendicular, that lies in the page because V is pointing into the page. So this vector lies in the page and it's perpendicular to V and to R, and the vector is upward. Okay, so that's obtained by the right-hand rule. So try it a few points here and you will see that these magnetic field lines directly above the charge, the moving charge, are in fact circles. Okay, if you look at each point, the magnetic field, and we did it at all the points around the loop, the magnetic field lines are circles. So let's get another little more practice with the right-hand rule here. So suppose we have a negative charge, and the negative charge, an electron, it's moving to the right. And we want to know what is the direction of the magnetic field due to this moving electron at the location of the dot. Okay. So the first thing we always do is we have to take the cross product of V cross R. So here's V, here's R. We take V and we point our hand along V. This is so hard to do with this camera. Take your hand, point it along, your fingers along V with your palm toward R. Okay. And if you do that, the vector V cross R, which is given the direction is given by your thumb. So again, take your fingers, point them along V with your palm pointed along R, and your thumb gives the direction of V cross R. And we see that the direction of V cross R points into the page. However, Q is negative. Okay? So what that means is when we tack on a negative sign here, that means that B is anti-parallel. It's in the negative of the direction of V cross R, which would be out of the page. Okay? And so the magnetic field due to the electron at this location would be out of the page. Okay? If this were a positive charge, Q, instead of a negative, like a proton, if it were a proton, then the direction of the field would be into the page, whereas with an electron, it's in the opposite direction. So again, we always take the cross product, V cross R, to get our direction, and then if the charge is negative, you have to flip it, the direction. Okay. So little bit of notation here. Since most of our vectors in this chapter are three-dimensional, and that means if two dimensions are in the paper here or the screen, the third dimension has to lie into and out of the screen. So we need some symbolism for denoting vectors that point into the page and out of the page. And so we're going to use the arrow here. And so for vectors pointing into the page, we will denote that by the tail of the arrow as an X. And for vectors pointing out of the page, the notation will be the tip of the arrow, which is coming out toward you. So vectors out of the page, tip coming toward you, will be denoted by these dots, and vectors pointing into the page will be denoted by the tail of the arrow, meaning the tip pointing away from you into the page, and that'll be denoted by the X. So we're going to be using this notation for the vectors pointing into and out of the page in the rest of the chapter here. Okay, let's do another class exercise here. So suppose we have a positive charge moving straight out of the page, okay? It's coming straight at you out of the screen here. And we want to know what's the direction of the magnetic field at the dot. Okay, so charge coming out of the page toward you. We want to know what the field is at the dot. And so this vector r will point from the charge to the dot, meaning to the left. Okay, so first thing we always do is we have to apply the right-hand rule to get v cross r. So you take your hand and you point your fingers out of the page, out of the screen toward you, with the palm toward the point of evaluation R. So hands pointing out of the page, palm pointing to the left, and that gives V cross R is pointing downward in the page. Okay, so that gives the direction of V cross R. Now the direction of Q is positive, and so B will point in the same direction as V cross R, which means downward in the page. Okay, if this were an electron, we would have to flip it, and that would give us a direction upward for the magnetic field. So you should be getting a little better by now, a little more comfortable, although it still takes some practice with the right-hand rule. We'll just continue to get more practice as the chapter goes on. Okay, now let's try an example here. So suppose that you have a charge, a proton, so it's a positive charge, and we have it moving upward along the y direction, and it's moving with a speed 2 times 7 meters per second. And the proton right now is located at the position x equals 1 centimeter, y equals 1 centimeter, z equals 0 from some origin. Okay, so here's the charge. It's at this position and it's moving along the positive y-axis. And what we want to do is we want to determine the magnetic field at the dot here. So at the location x equals negative 1 centimeter, y equals negative 1 centimeter, z equals 0. We want to know the field magnitude and the field direction. So we need to apply Biot-Savart. So as always here, we look at the equation here. We have to first write v as a vector, and then we have to write the unit vector r as a vector, because we're going to take the cross product. And then we need to get this distance r from the source charge to the place where we're evaluating the field. Okay. As an alternative, we could have used the magnitude of Q, the magnitude of V times the sine of theta, but we don't know theta, and by the time we're done calculating the magnitudes, it would be easier to just take the cross product in Cartesian coordinates. So you can try it the other way for fun, but we're going to write V and R in terms of their Cartesian coordinates. Okay, so V is equal to 2 times 10 to the 7 meters per second. It's traveling along the plus y direction, so we denote its direction by the unit vector j hat. Okay, that means that's in the y direction, positive y. Now we need to get the magnitude of r. So how far is it from the charge to where we're evaluating the field? So we need to use Pythagorean theorem, and the distance along the x-axis is 2 centimeters. The distance along the y-axis is 2 centimeters. And so we sum the squares and we use Pythagorean theorem, and we get that the field where we're evaluating the field is at 2.83 centimeters from the location of the moving charge. So the magnitude of r is 2.83 centimeters. Now we need to make our unit vector, and this is easy once we get the magnitude. First we write down what r is, and then we divide it by its magnitude. And this vector, which points from the source charge to the place where we're evaluating the field, is equal to negative 2 centimeters along the I direction and a negative 2 centimeters along the j direction. So that's r. R is the vector point going from the source charge to the location of the field. Okay. Now that we have R and we have its magnitude, we divide each of the components by its magnitude, and we get that the unit vector R is negative 7.07 along the I direction, minus 0.707 along the J direction. So now we have the unit vector R, we have the magnitude R to plug in the denominator, and we have V. Okay, so next we need to take the cross product. Okay, so here we plug in V, 2.0 times 10 to the negative 7 meters per second, and we have the unit vector R, which is negative 0.707 meters along I, minus 0.707 along J, okay, or centimeters, sorry. And then we divide that by the magnitude, which we put in meters, 2.83 centimeters. And we take the cross product, and you can do this. You get J cross negative I gives K, and J cross J gives 0 because they're in the same direction. And we get that the magnetic field strength is 2.83 times 10 to the negative 16 teslas along K. So I went through this a little quickly at the end, but I encourage you to go through it, and we can go through it during the synchronous lecture on Monday if you have more questions. But this, again, is where you need to know how to do the cross product. So look over the notes from yesterday and stop by if you have any questions. So there's another example, 29.1 in the text. So you should be able to do this on a homework or on an exam. So once we have the magnetic field due to a current, due to a point source of current, a moving charge, we can apply superposition to calculate the magnetic field due to many moving charges, for example, a current in a wire. Okay? So what we're going to do now is we're going to cast this result into a form for a current carrying wire. Okay? So consider first an amount of charge delta Q, and it's moving to the right here with velocity V. And suppose this delta Q is contained in a small length delta S of this wire. Okay. So if this segment is short enough, we can approximate this amount of charge delta Q in the segment as a point charge. And we can write the term Q times V in the Biot-Savart law as delta Q times V. And V, the velocity, is equal to delta S over delta T, and so we can plug that in. And we can place the delta T and under the delta Q instead of here, and then we use the definition, delta Q over delta T is the current I passing the point, and we can write Q times V as I times delta S. And so we just write that in Biot-Savart law. And now we get the form of this equation for a small section, delta S, of a wire that's carrying a current I. And so this is the magnetic field of a short segment of wire. Okay, so you might say, okay, well, why is that very useful? Well, the main use is that we can model a long wire, which is a realistic wire, in terms of many little short wires, and we can apply superposition as the sum of all the magnetic field contributions due to all of these little elements of current. So a long wire is just a sum of all these little segments. And your author does this in example 29.3, and he shows that the magnetic field strength, the magnitude of B, due to a long straight wire is equal to mu naught I over 2 pi r, where I is the current in the wire and r is the distance from the wire to where we're evaluating the field. So it's the distance from the wire to some point from the wire. So we see that the magnetic field strength depends on the current. So if we increase the current, we can get a very strong magnetic field outside the wire. And it goes as 1 over r, which means if we double the distance from the wire, the magnetic field is only half as strong. It goes as 1 over the distance. If we triple the distance r from the wire, it's only 1/3 as strong as it is at the wire. Okay. Now to get the direction, we can apply the right-hand rule. Okay. And since by definition we have Q moving in the current is in the direction of positive charge movement, and we have the charges moving, the current is to the right. This velocity here, the current right here is going to the right. The velocity of these positive charges is to the right. And so let's try an example here using the right-hand rule. So calculate the field at the point directly above the wire. Okay, so here V is going to the right, R is from Q to where we're evaluating the field, which means R points directly upward. And if you take your hand pointed in the direction of the field, with your hand pointing toward R, you get that your thumb points out of the page, and that gives the direction of the magnetic field above the wire. And you can go below the wire, and now you have R pointing downward, and you get that the field points into the page. And you can show at all these other points, you can calculate the magnetic field using the right-hand rule, and you can see that the magnetic field lines are circles surrounding the wire. So here's another method which is entirely equivalent, another right-hand rule for determining the magnetic field, and it works for current-carrying wires, okay? The right-hand rule we've been using always works, but sometimes it's a little clunky to use when you have wires, and so there's another form of the right-hand rule that's easier to use for a current-carrying wire to get the magnetic field. And this one's easy. So just remember it only works in some cases. Okay, so take your thumb and point it in the direction of the current. Okay. Then you curl your fingers around the wire, so it's as if you're holding the wire in your hand. And your fingers will point in the direction of the magnetic field lines around the wire. So in this case, the current is coming upward. You curl your fingers counterclockwise, and that gives the direction of the magnetic field. Okay, so the field lines are always going to be circles. It's just using this rule will help you determine whether they're clockwise or counterclockwise. And you can apply the right-hand rule, and you can show that if the current were moving in the opposite direction, meaning downward in the page, that the magnetic field lines, instead of being counterclockwise, would go clockwise. It'd be in the opposite sense of right here. I'm getting my sense of direction all messed up. And so here's our summary for a magnetic field due to a long current carrying wire. Okay, the magnetic field is proportional to the current. It's inversely proportional to the distance r from the wire along any direction. And the field lines are circles surrounding the wire with the magnetic field direction, either clockwise or counterclockwise, determined by the right-hand rule. And if you're drawing the field lines, as you will be expected to do on an exam or a quiz, the density of field lines is greatest where the field is strongest, so the lines are closer together near the wire, and they're further apart, field lines are further apart, further away from the wire where the field is weaker. So another example here with the right-hand rule. So suppose that you have the magnetic field of a wire, and the wire's carrying current, and the magnetic field is given by this direction in the figure. So in other words, to the right of this wire, the field is coming out of the page toward you, and to the left of this wire, the field lines are going into the page, or into, screen, away from you. Okay? So we're going to try the right-hand rule. There's two choices, right? The current either could be pointing downward in the figure at this point or upward. I mean, the current could either be going up along the wire or down. So let's try. I'm going to assume it's going upward. So put your thumb upward. Doesn't give the right field, because in that case, the curl of my fingers is coming out of the page to the left and into the page to the right, and we know that it's going the opposite. And so you can point your thumb the opposite way, meaning downward, and you'll get the right field directions. So in this case, the current is going downward in the figure here, toward the bottom of the screen. As a final example, let's do an example of calculating the magnetic field strength due to a long wire. And in particular, let's calculate the field strength due to an electric transmission lines. Okay, these lines, the power lines that carry electricity to your home. Okay, so although the evidence is weak, there's been concern in recent years over the possible health effects of magnetic fields generated by electric transmission lines, the power lines, okay? And so let's plug in some typical numbers, and let's see what the magnetic field strength is at the ground due to these transmission lines. And then we're going to compare it with the magnetic field due to the Earth, which is about 50 microtesla, or 50 times 10 to the negative 6 Tesla. So to do this, we need to know, for the field to a wire, we need to know how far is it from the wire to the ground, which is R, and we need to know the current I in the transmission line. And so we're given that. We're given R is 20 meters. So these transmission lines are about 20 meters above the ground. So R is 20 meters, and they carry on average around 200 amps of current, a lot of current, okay, at a potential of 110 kilovolts. We don't need that. We need the current, and we need the distance. So let's calculate the magnetic field strength on the ground 20 meters below the transmission line. So we plug in I is 200 amps, R is 20 meters. We multiply by mu naught, which is 4 pi times 10 to the negative 7 Teslas times meters times amps. Amps cancels amps. Meters cancel meter. And we get 2 times 10 to the negative 6 Teslas, or 2 microteslas. Okay. Now let's compare that with the field strength at the ground due to the Earth's magnetic field. And the Earth's magnetic field strength at the ground is typically about 50 microteslas. So the transmission line's strength, the strength due to that should be 50, that's a typo, I'll fix that, is only 2 microtesla divided by 50 microteslas is 0.04, or in other words, the field strength due to the transmission lines at the ground is only about 4% of the Earth's magnetic field, okay? So in other words, if you stand there on the ground with a compass, your direction of the magnetic field would not be moved much with respect to that by the presence of the current going through the transmission line. That magnetic field would not significantly alter the field due to the Earth, as seen by the compass, the direction. So you should be able to, we're done now with this, and we're going to go on in the next section on Monday by calculating the current magnetic fields due to current loops and solenoids. And then we'll move on to magnetic forces and the magnetic forces experienced by moving charges. So that pretty much ends it for this week, and we will see you on Monday. Have a great weekend.